Welcome back. We're on worksheet 3 in the energy unit on number 5 here. I'm going to give you the full-blown interior thoughts of what's going through my mind and how I figure out one of these guys. So let's read it. The bullet strikes a block of wood which exerts an average, on average, a force of 50,000 newtons opposing the motion of the bullet. How far does the bullet penetrate? Now this is actually like a really classical physics example and also something that we actually really do in real life. If you want to figure out how fast a bullet, usually it's how fast the bullet is going initially. How do we actually calculate that? We actually fire it into some sort of block, and we take some other measurements like how far the block moves, or if we put this on like a big string here and it actually like swings out this way, and then we measure like the angle that it gets up to and such. And we do energy calculations to be able to figure out the original velocity there. That's a little bit harder to do, so we're starting a little bit differently here, a little bit more simple. But it is a very classical thing. So fire a bullet into some sort of block and it like embeds itself, as you can kind of see here. It pushes itself into that block a certain amount of distance there. All right, in this case, we're given the amount of force that the block is putting on that bullet there. And let's go do an LOL diagram. So first, define my system. I'm going to go ahead and make the block of my system. I kind of want like a fuchsia color or something. Let's see if I can get like a... Ooh, yeah, I'm going to do that one. Let's do block. Oh, that's not too much different. And we'll go ahead and... I see that the height isn't changing here, or at least it's not like the instant before it goes in and the instant and then after it comes to a stop, that little bit there, it's not going to be like dropping an appreciable amount that I'm going to have to like worry about. If the picture's a little bit misleading, because if like I fired it like way over here, yeah, I would agree. It would like most definitely like drop some amount and then go in. But we're just looking at the velocity just before it hits the block and then the velocity after it stopped inside the block. So it's really just when it's traveling inside the block there, which you can imagine probably isn't that far into a block, and it's not too far. That would be less, it would be measured in like an inch, maybe 2, maybe 3 at the most. Depends on the bullet and the gun, obviously. But it's not too far, so that means the height-wise here, the height change is going to be basically minimal. So basically we're saying the height change is going to be 0 here. So that means that I don't have to put the Earth in my system if I don't want to. I can, and there wouldn't be anything wrong with doing that. But the point here is that I don't have to worry about the gravitational potential energy changing. Okay, so the height is going to be 0, and I can go ahead and I could say that this height right here is my 0 gravitational potential energy. I don't need that not there. It's just gravitational potential energy is 0. If I can erase, oh gosh, there we go. 0. Okay. So then what's going on with the energy? Well, at the beginning, it's going real fast there. So that's going to be a whole lot of kinetic energy because it's going super fast. 5. And at the end, we know that the velocity is 0 there, so that's going to be 0 kinetic energy. So then where's this energy go? Well, does it go into elastic energy? Do we have an elastic object? Is a bullet elastic? Bullets don't seem to bounce like a rubber band or a bouncy ball, bounces or elastic like that. I agree that they can like ricochet off of things. That's a little bit different. Is the block elastic? Well, it definitely deforms there like elastic objects do, but there's something else that elastic objects do. They don't just deform, they also reform. Is that block going to like reform? Is it going to reform and then push the bullet back out? No. So that block is inelastic, meaning not elastic. So it doesn't seem like we have elastic energy here then either. Chemical energy? Well, we definitely have a chemical reaction going on when we fire that bullet, but that's not the scenario we're looking at. We're looking at right here when it goes from before it goes into the block and after it goes into the block. Is it like a chemical reaction happening there? You'd say, well, no, a chemical reaction isn't happening. Is something going on with the bonds there? Well, if you're actually like, moving and breaking that wood in there, you're actually like destroying some of the bonds in there. So you are actually breaking a couple bonds in there. But we wouldn't necessarily say that's like a big chemical reaction or something that's happening there. But as it goes in here, we're going to have like friction rubbing across the top of that surface, the bottom of that surface, and me just deforming that wood. That's going to take some effort, you might say, energy, truly. And to do that, yeah, maybe things are going to start heating up, because I think back to the atomic level model that we've seen before and go, hey, that front of the bullet here, here's my bullet. When it goes and runs into the molecules, let me get a different color here. When it runs into the molecules of the block there, it's going to be like shoving all of these guys this way. Wait, hold on. And then those guys are going to compress, and then they might like wiggle and jiggle all of these other ones. So we have this big normal force that is on those block particles. And we also have then the same big normal force that's on those bullet particles, right? These bullet particles are real particles or real molecules as well. And so they're getting shoved around. And just that compression of those two guys hitting each other also heats things up, as we've seen before. Okay, so that means that no for chemical energy, but yes for thermal energy. Okay, so that's how I figured all of that one out. And the more I do of these, the kind of faster that whole thought process goes there. Okay, so again, that's kinetic friction across the top side of that bullet there and the bottom, as well as it running into other things and then deforming that thing. And whenever you do that, you're wiggling and jiggling all those little atoms and molecules more, and that is thermal energy. Okay, so now what is this saying? Well, we can go interpret this. We have that kinetic energy at the beginning here is equal to the thermal energy at the end. Let's see how we go and figure this one out. Well, kinetic energy, we do have a formula for that. That's 1/2 mv naught squared. Great. Let's think about that. We do have the mass there. We do have the original velocity. Great. Thermal energy, I don't have any formula for that. But I can figure out this, and so I can actually figure out the number that's associated with the amount of thermal energy. But this says something different. How far does the bullet penetrate? And penetrate what? Penetrate the block there. And now I think about this more and I go, wait, hold on a second. If, I did block there. I meant to put bullet there. I don't know why I did that. Is that how you spell bullet? Yes. Yeah, we did the bullet before. And then I go, okay, yeah, when this thing is heating up, yeah, the bullet would heat up, but also the block would heat up. So if I'm putting thermal energy in there, I really would need to put the block in here as well. Okay, so maybe that's why we wrote block before. I was like getting ahead of myself because I've done these too many times. Okay, so then I got bullet and block in there, and you can change your system as you're going along and figuring this thing out, but make sure you're not dynamically changing it all the time. You're getting one set system for the energy diagrams that you have here. So then, well, how do I figure out the far? How far? How far? That sounds like a distance. The better way to say that is, oh, maybe there's like a delta x here that's displacement. Right? And I think, and I interpret like these words here in different ways to then help prime myself of what it could lead to. And I go, okay, there's a delta x that this thing travels here. And we're talking about energy and delta x, and they gave me a force here. Is energy, delta x, and force related at all? Wait, I do remember that. That's like a force dot the delta x. Wasn't that something? What is that equal to? That's equal to some sort of work. Oh, right, what is work? Work is just the change in energy. Fancy name for change in energy. Oh, okay, great. So do I have a change in energy here? Well, yeah, sure. I have a change in both kinetic energy and a change in thermal energy there. Okay, great. So then this change in energy, could I say it's the change in thermal energy is just some force through some displacement there? Yeah, that's exactly what any change in energy is. It's a specific change in energy, and which is also work as well. Okay, so then, well, now I know this number, the force, gives me that 50,000. Do I know delta UT for the change in thermal energy? Well, yeah. Well, what was it at the beginning? We said it was 0. I forgot to write 0 in there. We said the kinetic energy, or the thermal energy, I'm sorry, was 0 at the beginning, and then 5, or the full amount afterwards. So then the change is just equal to, I'm going to switch back to colors. The change is just equal to whatever that original kinetic energy is, just as we said in this statement right here. The original kinetic energy is equal to the final bit of the thermal energy, and the beginning bit of the thermal was just 0. So then in this case, yeah, we just have, if you wanted to write it out more mathematically, it'd be the ending bit minus the beginning bit, and we said the beginning bit was 0. And so it's just the ending bit is equal to the force through some displacement there. Now I look at that and I go, oh, that's dot, the delta x. What does the dot mean? Well, that means it's the force that is parallel to the delta x. That's it. And now I think about this, and we did a little half free body diagram here, and we said, hey, the force here is the normal force that's on the bullet, or the normal force that's on those molecules in the block there. Put that extra little molecule in. And then, hey, maybe on this diagram I can put in the displacement. What's displacing the bullet is displacing this direction here. And now I look at the force here and the delta x. Are those parallel? Well, they are. So now it's just multiplying those parallel bits. That's it. That's as complicated as it gets. And now I go, hey, I know UT, I know that force, and I'm just solving for the delta x. So I kind of ran out of room right there, so I'm going to move this up to the line right there. And I'll go UT, let me divide by that force there, divide by that force, and that's going to be equal to my delta x. So then what is this stuff? Well, you could go and calculate UT right here if you'd like. I'm going to go ahead and I'm going to do it like this, and I'm going to use all of those guys because I know whatever I multiply there, which is just the 25 and the 350, I'm going to put that number over there. So I'm going to go put that number over there. Let me do it in that color actually. So I'll do the 1/2. So I'm just replacing UT with what it actually is, the 1/2 mv naught squared divided by some force, and that's equal to how far that thing goes. I guess I should do these guys in green. Maybe I shouldn't be so particular. Force and then delta x. All right, so now let's think about what numbers we're going to put in, and I'll do that in blue over here. So what numbers are we going to put in? The mass. The mass is what? 25 grams. Wait, hold on. Are alarms going off in your head? There should be. There should be like a blue light or a red light in your head going, wait, there's something amiss here. I see mass, and I see it in what unit? That's in grams. We've always been doing mass in what unit? What is the standard unit for mass to get all the other units out that we would expect? It's not grams, it is kilograms. We need to convert that into kilograms. Okay, cool. Just like we've always done. All right, so then I got to ask myself, kilo, how many grams are in a kilogram? Kilo means 1,000 there, so 1 kilogram is 1,000 grams there. And so that means if I have grams and I want to get to kilograms, I need to multiply or divide by 1,000. Which one is it? Easy way to do that is when I go and convert mass into into kilograms, should I have a ton of grams per kilogram, or should I have just a very small amount of grams in a kilogram? Well, I know that I have 1,000 of those grams in there. So when I go from the small unit of a gram to a big unit of a kilogram, I should have a small number of kilograms there. And the only way to make that thing smaller is to divide by 1,000. And so I am going to divide by 1,000. And that's pretty easy to divide by 1,000 there, because I just have the decimal point there, and I go over 1, 2, and then 3 bits there, because I have 3 zeros there, and that's the easy way to do that. So then I can see that I have 0.025 kilograms is now the mass. Now you can pick up your calculator and do that as well. So then I erase that there, and I go, that's 0.025 kilograms for that guy. My original velocity is 350 meters per second. Is that the right unit? Yes, it is, meters per second. And then the force there, we said they gave it to us at 50,000 newtons. Is that an okay unit? Yes, it is. And so now I just put in all of that stuff, and I solve for delta x. Grab your calculator, do that with me. And I get delta x is equal to 0.03, 0.030625. And I'll just round it right there. 0.03 meters, and it's just in meters. We know it's going to be just in meters because I used all my other standard units there, and so I'd get the standard units out. If you go and cancel out those units, they actually do come out to be meters there. Did you get that? Careful, make sure that you squared that velocity. That's an easy one to miss there. Cool, that's it. Have a beautiful day.